Hello everyone, my name is Wenxuan Peng. I'm a senior computer science student at Nanyang Technological University in Singapore. This summer, I worked with Dr. Jane Oh as well as my mentors Peter and Zhixuan at Carnegie Mellon University Robotics Institute Summer Scholars Program on a project titled PCSG, Personalized Comic Story Generation. Now let's get started. Today's presentation will start with objectives and then dive deep into the challenges we face in the current realm of story-to-comic generation, setting the stage for the overview of our PCSG model. Subsequently, we will explore how our PCSG model works with detailed model architecture. Next, we will work through some of the examples of the results achieved with our model, followed by a discussion of our future work. Finally, we will wrap up with our conclusions. To begin with, imagine a world where AI can be used effectively to help us generate our own personalized comic visual stories. What if we could just provide a plot, characters, and even specify the scene and have an AI bring it all to life? This is the vision that we're excited about and working towards. Firstly, personalization. Our aim is to develop a tool that allows users to create unique, appealing comic stories based on their individual ideas and desired characters. Secondly, controllability. We want to give users detailed control over the design of each panel. This means you're not just telling the story, but also shaping its visual presentation to your exact liking. Next, consistency and diversity. We're working on a system that supports diverse elements in our comics. For example, different views, angles, poses, while maintaining high fidelity. This would add dynamics to your stories without compromising on visual continuity. Lastly, the concept of composability. We aim to build a system that can accurately integrate multiple concepts into rich, engaging narratives. Here we also show an example to demonstrate the 4 key points. However, although current text-to-image models have made incredible strides and are becoming increasingly powerful, they do fall short in a couple of key areas that we hope to address. The first shortcoming is the black box operation. Right now, these models operate in a way where you give them a text input only and they spit out an image. The problem is this process doesn't really give users the control to shape the output as per their vision. The second issue is with composing multiple concepts. The model often struggles when asked to handle multiple concepts at once. They can lose objects, get the relations wrong, or fail to create the desired interactions. So, while the text-to-image models are improving, these issues limit their effectiveness for visual storytelling. Now, while the existing text-to-image models have their limitations, recent advances in visual storytelling have tried to address these problems. Despite these efforts, there are still critical issues we need to tackle. The first issue is limited personalization. Current methods are evaluated on relatively simple story datasets and often struggle when it comes to user-customized scenarios. There have been efforts to improve personalization, particularly around faces, but these often end up being low quality. The fidelity is not well preserved with just face imprinting in this work. The next problem is lack of diversity. While there is a focus on maintaining character consistency, it often comes at the cost of diversity in character representation. There is a tendency towards default poses and front-facing views, with a struggle to depict characters in a variety of views, angles, poses, and scenes. Here are examples illustrating this issue. It's clear that while the characters remain consistent, the lack of diversity in the representation limits the expressiveness of the story. In fact, it results in overly simplistic plots that are unable to accurately portray more interesting and complex narratives. But fear not. This is where our proposed solution, PCSG, comes into play. We've designed PCSG to tackle the limitation of current models and empower users to create personalized visual narratives. So let's revisit our goals in light of our solution, PCSG. Our aim was to enhance personalization, improve controllability, ensure both consistency and diversity, and promote accurate composability. As you can see from the current results we can get, PCSG brings all these aspects together in a powerful and effective manner. So now let's dive deeper into the architecture and pipeline that make this possible. To begin with, how to control and generate a specific panel in our comic stories. Given a prompt, the girl is holding her cat in front of her computer. We compare the results of current state-of-art Stable Diffusion XL model and our PCSG model. We will now break it into steps and see how we can generate this panel. To lay the groundwork for PCSG, we rely on the latent diffusion model as our backbone. Latent diffusion models, designed for handling high-dimensional data like high-resolution images, employs an autoencoder to transform images into compact latent representations. The diffusion process occurs within its latent space. Here, noise is incrementally added to these latent representations over time, and then a UNet model is employed to predict the noise, and then be utilized to denoise from a noisy image and generate high-quality images. Text inputs are used to guide this generation process. They are first transferred to clip embeddings and then feed into the cross-attention layers to interact with image spatial features. However, while this setup is powerful, it's not perfect. Text-only inputs cannot always provide all the necessary details for our task. Let's look at this example. If I ask Stable Diffusion to generate comic of a girl is touching her cat in front of her computer, we see the model misinterprets object relations, loses important details, and doesn't accurately realize what user had in their mind. Firstly, to maintain a consistent and unique identity for each character across panels, we leverage a technique called low-rank adaptation, in short, LoRa. It introduces low-rank matrices in MLP layers of self-attention and cross-attention layers. This technique helps us adapt our model without overfitting or forgetting previously learned concepts. To further enforce character uniqueness, we develop character-specific tokens using a strategy that leverages real-world tokens, inspired by Dream Boost method. This strategy lets us associate unique tokens with individual character identities. For example, here, enemy SKS girl. The weights obtained via LoRa are utilized in this process. You can see we are able to preserve character identity with only training a very small amount of weights while freezing the original model. However, we also notice the limitations. The character representation is not very diverse, with mostly front-facing views similar to our training images, and the model still struggles with accurately composing other concepts. So, to both preserve character consistency and compose multiple objects within one image as user wants, we also introduce a layout-to-image module. This part of our unified model enhances spatial control. It takes semantic data and spatial configuration for each comic entity. User can define the position and size of entities via a user-friendly bounding box input. The module generates a grounding token by fusing these data points and incorporates spatial grounding by introducing a new gated self-attention layer, positioned between self-attention and cross-attention layer in the original UNet model. By only training this gated self-attention layer, we are able to significantly improve the model's ability to position entities accurately within the panel and facilitates precise multi-concept compositions. However, we must also note that the control over layout alone is still not enough for generating high quality and visually appealing comic images. As we can see from the examples, characters are often squeezed into the bounding box region, leading to a loss of visual quality. Also, nuanced actions and poses can be difficult for the model to infer from text descriptions alone. To overcome this, we incorporate our third plugin, Pose-to-Image plugin, using the ControlNet architecture. It's adaptable, allowing our Stable Diffusion model accept additional visual input for control, such as pose keypoints. This offers precise and explicit control over character poses. The ControlNet creates a trainable copy of the original model's parameters, while the original parameters remain locked. Linking this ControlNet architecture to each level of the UNet in our system allows for a synergy of text, spatial, and pose controls. As a result, we can now generate higher quality comics with more detailed and accurate depictions of characters and their actions. Now, altogether, the three plugins attached to a unified Stable Diffusion backbone worked to generate highly personalized, engaging, and visually appealing comic stories, ensuring character consistency, user-defined layouts, and detailed poses in each panel. Moreover, when creating a coherent comic story, it's not just enough to consider each panel in isolation. Instead, each panel must be informed by both its specific caption and the preceding narrative context. Traditional text-to-image tasks can falter here, as they often assume conditional independence between each frame and don't count for this history and context. This can lead to disjoint and inconsistent comic sequences. To tackle this, we're developing an auto-regressive process that factors in the history of captions and scenes during image generation. This enables each panel to build upon the story so far, resulting in a much more coherent and engaging comic narratives. Now, based on all our conditioned inputs, prompts, layouts, and poses, let's see some of the current results generated by our PCSG model. We can see users are able to generate what they exactly imagine in their mind, while preserving the character's identity. Some more results here. So now we will be able to recap and understand how these results are generated. As you can see from the examples, given user, our model can handle various characters and styles, ranging from traditional comic book to Disney-style animation. What's more, our model ensures consistency and coherency across the comic panels, maintain the identity of each character, preserve their unique features and styles throughout the story. And it's not just about the characters. Our model also considers the wider context of the comic. We're still trying to maintain a high level of consistency in the background and plot elements, adapting this as narrative evolves. As we look to the future, we have identified two key areas for future development. Firstly, we aim to refine character interactions in our model. The goal here is, when introducing more and more characters into our scene, we want to enhance the complexity of these interactions while reducing feature mixture. Secondly, we're targeting improvements in background and object consistency. Currently, our primary focus has been on main characters. However, to generate more coherent and visually consistent comics, we need to extend this consistency management to backgrounds and objects across panels. These enhancements will allow us to push the boundaries of automated comic generation further, creating more intricate, engaging, and visually consistent comics. So that's all for my presentation today. We thank Rachel Brazin, John Dolan, and all of Carnegie Mellon University's Robotics Institute Summer Scholars Program. Thank you.